Number 39. A playground merry-go-round has a mass of 120 kilograms and a radius of 1.8 meters, and it is rotating with an angular velocity of 0.5 revolutions per second. What is its angular velocity after a 22 kilogram child gets onto it by grabbing its outer edge? All right, the child is initially at rest. All right, so here's our merry-go-round. It has a radius of 1.8 meters. The angular velocity is 0.5 revolution per second, and the mass is 120 kilograms. Before I even approach anything, I know I'm probably going to have to convert these units. I need to get rid of revolutions per second. I got to get radians per second. So let's just get rid of that. Let's just do it now, all right? Let's do the, it's like grandma's rule. You got to eat your broccoli before you get to the good stuff, all right? So this is going to be radians. At least that was my grandmother's rule. I don't know. Anyway, so now here we have, so 0.5 times 2 times pi. So we get a value of about, I don't know why I need to plug that into the calculator. Oh man, half times 2 is 1, not nothing. And obviously this is just now pi. I'm just going to leave it in terms of pi for now, radians per second. Okay, so this is the angular velocity. So, okay, now that that's out of the way, now I'm going to try to think about what conditions are held true in this problem, right? Now, anytime we have changing conditions, okay, meaning that we have the merry-go-round rotating without the child, and now the child's going to jump on, and we got to figure out what the velocity is, the angular velocity that is. After the child jumps on, you want to think and identify, is anything staying constant? Is there any conservation principles operating here? All right, and there is, right? There's a law of conservation of angular momentum. All right, just like the momentum problems you've done in your other chapter, this is pretty much the same thing, just dealing with angular momentum now. So I'm going to look down here on the bottom right, and I'm going to just box in my angular momentum formula. Now, what this that's the formula that relates the angular momentum to the moment of inertia and the angular velocity. However, I'm going to definitely be using that equation, but let me start with something even more general, right? I can say that the angular momentum before the child jumped on the merry-go-round is equal to the angular momentum after the child jumped on, okay? So we have to think about the nature of this situation. So the merry-go-round has a certain angular momentum before the child is on there, right? That would be equivalent to the moment of inertia of the merry-go-round without the child, because the child's not on there before it jumps on, right? I mean, that should be apparent. And that will then be multiplied by the angular velocity before the child jumps on, okay? So they basically told that to us already, right? It's going to be just the pi radians per second. So now that will equal then the moment of inertia of the system after the child jumps on, okay? So after the child jumps on now, the moment of inertia is basically, if we think about this, right? There are basically two components to it now. It's the merry-go-round that's revolving, and it's now the child that's also rotating. So I'm going to say this is now the moment of inertia of the merry-go-round plus the child. Okay? Will then be multiplied by the final angular momentum, or the angular momentum after the child jumps on. Now, we are after this variable. Okay? So just solve it for that for right now. It should be fairly straightforward. So the final angular velocity will then be equal to the moment of inertia of the merry-go-round multiplied by the initial, or angular velocity, meaning the angular velocity before the child jumped on, all divided then by the total moment of inertia of the merry-go-round plus the child. Okay, so this is the formula. Now we can start to break things up and find more variables in here. All right, let me just move this on over to the side, give myself a little more space. So now let's start breaking up the moments of inertia. Okay, so the moment of inertia of the merry-go-round. Well, what is the merry-go-round like? All right, you have to approximate it. One of the formulas that you're familiar with for moment of inertia, right? So this would be best approximated by a disk rotating around its center axis. And do you remember the formula for that? Okay, the formula is going to be the, not I anymore, but it's the mass of the merry-go-round multiplied by the radius of the merry-go-round squared, all divided by 2. Okay, so that's going to be the moment of inertia. Then that will then be multiplied now by the angular velocity before. Okay, so I'm just going to leave that multiplied by angular velocity before. And this whole thing now will be divided by the combined the combined moments of inertia. So we already know that it's the moment of inertia of the merry-go-round, which is mass of the merry-go-round multiplied by the radius of the merry-go-round squared, all divided by 2, plus now, okay, the moment of inertia of the child. So in terms of the nature, what's the mass of the child once the child jumps on here on the merry-go-round? They're on the periphery. Their mass, we can assume it's kind of like a point mass on the periphery, and it's rotating around the merry-go-round. So what shape best approximates that? Well, it sounds like it would be the hoop, right? The hoop with the center axis. So that one is just simply mr squared. So this one will be the mass of the child, right, multiplied then by the radius of that mass where the child's located squared. And that's it. Now here's the formula. We know everything, so we can plug everything on in. Isn't it beautiful? So now the mass of the merry-go-round was 120. Okay? 120 kilograms multiplied by the radius, which was 1.8. That whole thing squared, all divided by 2. Multiplied then by the angular velocity before, which was just pi radians per second. This whole thing then divided by now the 120 times 0.18 squared over 2, plus now the mass of the child, which is 22 kilograms, they told us, multiplied by the radius of that mass of the child relative to the axis of rotation, which is also the 1.8 meters. Okay, 1.8 squared. All right, so let's calculate. So we got 120 times 1.8 squared divided by 2 times pi. And I got about 610 for the numerator. Now divided then by 120 times 1.8 squared divided by 2 plus 22 times 1.8 squared. And what do we get? At about 2.30, right? So 2.30, and this is now going to be in terms of radians per second. And voila, there it is. Now, does it make sense? Well, yeah, it does, right? Because the initial angular velocity is pi, which is about 3.14159, blah, blah, blah. And the velocity then has gone down. And that should make sense, right? You would expect that as we add more mass to this rotating body, that the rotational speed is going to go down. All right, so answer should make sense. Guys, thanks very much for tuning in. Help us out. Hit that subscribe button. We want to bring more videos to you that help us out tremendously. And hit the like button too. All right, thank you so much. We'll see you in the next video. Take care.